Tasmania in the Lab. Michael Muthukrishna and I also wondered if we could create a Tasmanian-like phenomenon in our laboratory under controlled conditions. Using a design very similar to that described earlier for the transmission of image editing skills, we now trained a first generation of experts at tying a complex system of knots used in rock climbing. While wearing a head cam, each participant also made a video of how to tie the knots they learned. Novices in the next generation received the videos and their teachers' skill scores for the knot system. In the one model treatment, each novice received only the video and score from one person from the previous generation. In the 5 model treatment, they received the videos and scores from all 5 people in the previous generation. As with the earlier experiment, participants were paid for both their own scores and those of their students in the next generation. Remember, the first generation is composed entirely of trained experts, so we should expect skill levels to drop over generations. The question is whether social interconnectedness influences the rate of decline and final level of skill in the group. When learners could access only one model, knot tying skills plummeted rapidly relative to those who could access 5 models. By roughly the 5th generation, the two populations appear to be approaching a steady state, with the 5 model population sustaining a much higher average skill level than those in the 1 model population. As before, everyone in the 10th generation of the 5 model group is more skilled than the most skilled person in the 10th generation of the 1 model group. Maxime Derex's team also found parallel results using their experimental setup, as described earlier. As noted, the simple arrowheads improved over the 15 rounds in the larger groups. Meanwhile, the more complex fishing nets held fast at their initial performance in the big groups with 8 or 16 members, but deteriorated in the smallest groups, those with only 2 or 4 members. By round 15, this deterioration meant that the fishing nets of the big groups were 3 to 4 times better than those of the small groups. Among humans, the size of our social groups, the intensity of our sociality, and the density of our networks depend on social norms and cultural technologies like rituals. Even among hunter-gatherers, as we discussed in Chapter 9, it's the ritual partners and affinal ties that enmesh individuals within large social networks that stretch across many bands. When the ethnographers Kim Hill and Brian Wood specifically asked Aceh and Hadza whether they'd ever watched other members of their ethno-linguistic groups make a tool, the effects of ritual partnerships and affinal ties dominated, being more important than even close blood ties or physical proximity. These results suggest that the rituals, ceremonies, and kinship systems that expanded with the speakers of Inuit, Numik, and Pama-Nyungan languages were probably intimately tied to their sophisticated technical know-how. The sociality they engendered nourished and sustained their collective brains. The point is, if intergroup competition is favoring sophisticated tools and weapons, it has to favor the social norms and institutions that can sustain a larger collective brain. Technology and sociality have to co-evolve. Children versus chimps and monkeys. Small groups of 3- and 4-year-old children faced off against similarly sized groups of chimpanzees and Capuchin monkeys. The challenge was a puzzle box that was meant to provide an opportunity for cumulative cultural learning. In one version of the experiment, if individuals could perform a series of actions on the box in a specific order, they could receive increasingly desirable rewards with each correct action. The box had to be slid, pressed, and twisted in various ways. Capuchins and chimpanzees got a carrot for the first correct action, followed by an apple, and finally the coveted grape. The kids got better and better stickers. It's a nice task for our purposes, since it has the feel of the food processing techniques that I've emphasized had a real impact on human survival and evolution. Also, reference Chapter 16. The interspecies competition on this task, unlike many of the cognitive tasks I described in earlier chapters, was actually no contest. The kids ruled. 43% of the children got to the final stage, stage 3, whereas only one chimpanzee did, and none of the Capuchins. Overall, for each step of cumulative complexity above the first, the data suggests that 1,000 hours of access to the box yielded 1.7, 6.1, and 388.6 additional steps in complexity for the Capuchins, chimpanzees, and humans, respectively. This pattern is impressive, especially given the familiarity of the non-humans with these kinds of reward-containing puzzle boxes. Clearly, cumulative culture is our thing. What led to the success of the children? Among them, those who did better, 1. Imitated others more often, matched others' actions, 2. Received instructions more often, were taught, and 3. Received more gifts from others, were social. So, imitation, teaching, and sociality are what mattered. Meanwhile, the other species floundered precisely because they lack these social and cultural abilities. Chimpanzees and Capuchins revealed 0 instances of teaching or altruistic giving, whereas the preschoolers performed 215 acts of giving and 23 unambiguous instances of teaching. For imitation, chimpanzees did copy some stage 1 behaviors, but none for stages 2 or 3. These experimental findings fit nicely with observations of these primates in the wild, where researchers have found no clear examples of teaching or other tools that require cumulative cultural evolution. Innately dumber than Neanderthals? In class, I show my undergraduates unlabeled pictures of 4 different stone toolkits from 1. 18th century Tasmanians, 2. 17th century Australian Aborigines, 3. Neanderthals, and 4. Late Paleolithic modern-looking humans, 30,000 years ago. I asked them to assess the cognitive abilities of the toolmakers by looking at the tools. Remember, there are no names or dates, only images of stone tools. My students always rate the Tasmanians and Neanderthals as less cognitively sophisticated than both the 17th century Australian Aborigines and the late Paleolithic toolmakers. Of course, there's no reason to suspect any innate cognitive differences between Tasmanians and Aborigines, who only became separate populations after the Bass Strait flooded. Unfortunately, no one raises their hand to suggest that, actually, it's not possible to infer innate cognitive abilities from tool complexity because of the importance of sociality in generating tool complexity. That's the correct answer. To sharpen this point, consider whether the polar Inuit of 1820 were smarter than the polar Inuit of 1860. In 1820, they could make kayaks, fancy fishing spears, and compound bows. In 1860, they could not. Similarly, when many paleoanthropologists look at the differences in the sophistication of the toolkits produced by different species of ancestral humans, they sometimes make direct associations to the innate cognitive endowments of those species. Neanderthals provide an interesting case because they coexisted in Eurasia with our own African lineage and must have interacted in some fashion because many modern human populations carry some Neanderthal DNA. Because most Neanderthal groups possess a toolkit substantially less complex than the more modern-looking African intruders, our ancestors, the assumption has often been that Neanderthals suffered some innate cognitive deficits relative to the African immigrants. This has been argued consistently, despite the fact that Neanderthal brains were as big or bigger than our brains. In primates, the strongest predictor of cognitive abilities across species is overall brain size. Consequently, it's not implausible that we were dumber than the bigger-brained Neanderthals. Researchers, however, have typically proceeded under the assumption that our lineage must have been innately smarter, so the real question appeared to involve figuring out what subtle differences in our brains or our specific cognitive abilities, for example, language, would account for our relative success, our global domination versus their extinction. Let me toss out an alternative. Individually, the African immigrants, our ancestors, who were contemporary with Neanderthals, were a touch innately dumber. However, they had larger collective brains capable of generating greater cumulative cultural evolution. These larger collective brains resulted from bigger and more tightly interconnected social groups, as well as from individuals who experienced longer adult lives, on average. Longer adult lives means more time for learning, both from diverse other people to create novel recombinations, and from individual experience, as well as for retransmitting this wisdom to others, as I discussed in Chapter 8. More specifically, Neanderthals, who had to adapt to the scattered resources of Ice Age Europe and deal with dramatically changing ecological conditions, lived in small, widely scattered groups and periodically suffered shocks that reduced their population size. Adults often died young, usually from injuries suffered during hunting by, for example, engaging and surrounding dangerous prey like elephants, horses, and red deer with only thrusting spears. Meanwhile, the invading African immigrants lived in larger and more interconnected groups, perhaps due to some particular set of institutions that emerged in the richer, warmer, or otherwise more fertile climates to the south. For example, coastal marine environments. Many more of them lived past 40, probably due in part to their projectile weapons, making hunting much safer, and other superior cultural adaptations like high-quality warm clothing. Under the right ecological conditions, social norms can evolve to create institutions that permit a larger collective brain, which can in turn extend lifespan and further energize that collective brain. So Neanderthals may have needed those individually larger brains to compensate for their ecologically imposed smaller collective brains. The extra edge created by more individual brain power in Neanderthals would have been dwarfed by the power of social interconnectedness and longer lives on the collective brain sizes of the Africans. Because of their larger collective brains, this African population may have been able to invade and replace Neanderthals in Europe for the same reasons that the Inuit were able to replace the Dorset. A different environment of origin had fostered different social institutions that generated a more sophisticated and adaptable technological suite. Curiously, despite the extinction of the Dorset and the pre-Numic people of the Great Basin, no one has suggested innate intellectual inferiority. Thus, it's plausible that the Neanderthal replacement may have been just an earlier chapter in a cultural evolutionary story that has repeated itself time and time again over the history of our genus. To be clear, my argument is that cultural evolution has been driving genetic evolution for hundreds of thousands of years or longer. So I do think that we should expect that genetic differences existed between, for example, members of our species at 150,000 years ago and at 50,000 years ago. We were self-domesticating during that period. My points here regarding groups like the Neanderthals is only that you can't read innate intelligence out of the material record without knowing about the population size and interconnectedness, and that cultural evolution driven by intergroup competition was occurring then as now. This view of cultural evolution underlines another point about technology and our species' evolutionary history. It's not a straight line. Researchers look for the earliest evidence of things like fire, spears, hafted weapons, fishhooks, jewelry, trade, bone tools, etc., and then all too often assume that, once invented, these persist forever, or at least until they are replaced by something better. The expected picture seems to be one of continuous, if often halting, technical progress. However, all the evidence I've presented so far indicates that the flourishing of technology and non-material know-how will depend on the interaction of ecological conditions, environmental fluctuations, disease shocks, and social institutions. Groups can and will lose know-how and never get it back. Consider something as precious as bows and arrows. Current evidence suggests that bows and arrows may have emerged by 60 to 70,000 years ago in Africa, though some argue for a much earlier date. Meanwhile, at the time of European contact, there were no bows and arrows anywhere in Australia. An entire continent of hunter-gatherers relied on spears, throwing clubs, and boomerangs. We've already seen that the Dorset lost their archery expertise, which cost them when the Inuit arrived. Bows and arrows were also lost in Oceania, perhaps several times. Like ocean-going boats and pottery, it turns out that the know-how to make and use bows and arrows is frequently lost by human groups. As previously noted, some foraging groups have even lost the know-how for starting a fire. Because humans in the Paleolithic faced more extreme and more rapidly shifting environments than at any time in recorded history, we should expect technological evolution to appear erratic, with bursts of flourishing and then sudden crashes as populations were decimated, dispersed, or otherwise disconnected. This view is consistent with the data. However, the scattered and fragmentary nature of the paleoanthropological records still leaves a fair amount of uncertainty. Since it is far more important for a cultural species to be social than innately smart in producing complex technologies, when we see technological and other cultural flourishing, we ought to also consider the realm of the social, the institutions, marriage practices, and rituals, in trying to understand the origins of that cultural flourishing. By contrast, genetic explanations for cultural flourishing seek to link the complex products of cumulative cultural evolution, like languages, to genetic differences. However, the emergence of complex languages, far from being an ultimate explanation for cultural flourishing, represent merely one of the products of cumulative cultural evolution and is subject to many of the same forces as toolkits. We'll turn to this in Chapter 13. Tools and norms make us smarter. Collective brains make us individually smarter, even in the absence of any genetic evolution. Larger and more interconnected groups generate more tools, expanded bodies of know-how, and fancier techniques. These larger repertoires, once learned, equip individuals to solve, by themselves, more problems, including problems they couldn't otherwise solve. In the longer run, these culturally constructed worlds, filled with concepts, tools, techniques, procedures, and heuristics, will favor genes for more sophisticated cognitive abilities. However, let's put genes aside and assume them fixed. Cultural evolution will still make us smarter. To see this effect in its most basic form, let's start with chimps. Thibaut Gruber, Richard Wrangham, and their colleagues set up an artificial honey well among different chimpanzee populations and watched what the apes would do. The honey well was designed such that the chimps could access the honey, which they love, only by using a dipping tool, like a stick or leaf. Different populations of chimpanzees had been selected because some of them were known to engage in fluid dipping to obtain water from logs. The question was, would knowledge of the fluid dipping technique influence the ape's chances of figuring out how to obtain the delicious honey in this somewhat new context? Yes. Only chimpanzees from groups in which the practice of fluid dipping was common figured out how to access the honey. This remained true even when the researchers supplied a stick for the apes. Even when the chimpanzees found the stick already stuck into the honey well, a nice hint, still, only the chimpanzees from fluid dipping communities figured out the puzzle. So, the ability of chimpanzees to solve a novel problem depends on their culture. Now, imagine an ape who grows up in a world already filled with wheels, pulleys, springs, screws, projectiles, elastically stored energy, for example, bows, spring traps, levers, poisons, compressed air, blowguns, rafts, leasters, and heating, fire and cooking, just to name a few things. This ape has a head full of options, of prefab solutions, to apply to any new problem. These tools, or really concepts, may seem easy or obvious, but they are hard for us to innately figure out. Consider the wheel. The wheel was invented relatively late in human history, long after agriculture and dense populations had emerged, and only in Eurasia. It was never invented in the Americas, Australia, or New Guinea, despite the availability of llamas in South America and dogs everywhere to pull carts, and the general need for wheelbarrows, pulleys, and mills. Similarly, it appears that nothing using elastically stored energy was ever invented and maintained in Australia. That means no bows, stringed instruments, or spring traps. Tools using compressed air also appear to have been absent, which eliminates blowguns, flutes, and horns. Many of the products of cumulative cultural evolution give us not only ready concepts to apply to somewhat new problems, and concepts to recombine. Bows are projectiles plus elastically stored energy, but actually give us cognitive tools or mental abilities that we would otherwise not have. Arabic numbers, Roman letters, the Indian zero, the Gregorian calendar, cylindrical projection maps, basic color terms, clocks, fractions, and right versus left are just a few of the cognitive tools that have shaped your mind and mine. These have evolved culturally to fit the mental constraints imposed by the genes that build our brains by harnessing, enhancing, and recombining our innate capacities to develop new and unexpected abilities. To see what I mean, consider the abacus, a tool that has not shaped the minds of most Westerners. Skilled abacus users can solve math problems like 345 plus 675 plus 853 faster than calculator users. That's impressive, but it's really just one tool versus another. However, here's the thing. Skilled abacus users can also beat calculator users even when they are disarmed without their abaci. That is, they can make purely mental calculations faster than calculator users. This is because the abacus evolved from counting boards, which date back to before the Babylonians, through a long process of selective cultural evolution. Analyses of the abacus suggest that it is optimized to the constraints and affordances of our visual perception and memory, making it easier for us to store numbers in visual working memory. Once fully trained, people, including young children, can do super-fast mental arithmetic. They accomplish this by visualizing the abacus and often actually manipulate their fingers non-consciously as if they were rapidly sliding the abacus beads around. Language appears to play little or no role in the calculation, except that at the end, people have to report their answers in Arabic numerals or their verbal equivalents. The approach abacus users take to mental arithmetic contrasts with that taken by typical Western undergraduates who, when facing the same challenge, lean heavily on their linguistic tools, number words. Thus, the abacus provides a mental prosthesis that, by harnessing aspects of our visual memory, can deliver mental powers that seem almost unimaginable to those unfamiliar with this simple but elegant tool. As we turn to take a look at language, it's worth noting, however, that in doing mental arithmetic, both Western undergraduates and abacus users had to rely on the products of cumulative cultural evolution.